Hello. Yeah, thanks organizers for this cool workshop. So I'm Xiaohua Zhai, and this work is done with my colleagues, Alexander Kolesnikov, Lucas Beyer, based in Google Brain Zurich team. All authors contributed equally. So what is self-supervised learning? The goal is to learn useful visual representations from unlabeled data instead of the traditional expensive human labels. So why do we need that? There are billions of images and videos from the internet. So in theory, you have access to unlimited data. How to train a self-supervised model from those unlimited data source to beat self-supervised learning is the next milestone. So the main idea behind that is to formulate a pretext task from the unlabeled data itself without requiring labels. And it requires a network to learn the high-level semantic while solving the pretext task. So let's take a look at the concrete example. This relative patch location, given an input image, if we split it into 3x3 patches and given the anchor patch, and could you tell the relative patch location of 2 patches? So it's in theory, it's a 8-class classification problem. And you could train a network to solve this 8-class problem. And another example is rotation. So the network is asked to solve a pretext task of predict the angle of rotation applied to a given image. So it's intuitively simple and easy to implement. And it assumes that there's exactly one object in the image. So there are several challenges in this domain. The first one is if you want to train your own self-supervised learning, which architecture should you use? And which kind of self-supervised loss should you take? So we made a large-scale study in this area and made some recommendations. And we pushed the outdated AlexNet to using the modern ResNet. More results would be presented later. And another thing is it's hard to implement all of those self-supervised techniques because of shortcut. So network is pretty smart to look at some low-level clue or some watermark. For example, if you detect rotation, if you can detect the text, it's pretty simple. You can get 0 loss. But this network doesn't learn high-level semantic. So if you transfer this network to downstream tasks, it actually performs pretty bad. So we open source the reproducible code with a lot of tricks in this domain. And you could check our code from GitHub. So before diving deep into the numbers, I want to quickly mention the commonly used metric in this domain. So given a network, pre-trained network from unsupervised data set, people always extract the representation from a certain layer from the network, and using the frozen representation to solve a downstream task with linear regression or multi-layer perception network. So I want to show the recent advances in self-supervised learning. Starting from 2015 till 2018, around 4 years, there has been progress from around 32 on image in the top 1 accuracy to 42. So it's about 10% improvement during the past 4 years. And starting from last year, this shows a steep rise by switching from the AlexNet architecture to ResNet-like architectures. And here we would make a deep dive into the revisiting paper.
Let me introduce our study setup. So in our paper, we implement 4 prominent self-supervised techniques, which are relative patch location, jigsaw, puzzles, rotation prediction, and exemplar. On top of this, we implement 4 convolutional neural network architectures, which are VGG, ResNet v1, ResNet v2, and RevNet. More details are available in our paper. We consider variants of these architectures. So in particular, we vary the width and use widening factor 1, 2, 3, or 4. We try to keep or add the last ReLU layer to control the sparsity of the final representation. And we also implement a variant of VGG, which is very similar to ResNet, except for the fact that it doesn't have skip connections. And for evaluation, we use ImageNet dataset and places, and we also use either linear evaluation or we train MLP model on top of the pre-trained representation. So we have all the numbers. This is just a small fraction of the results we have, which illustrates the numbers for ImageNet evaluation with linear model for all self-supervised techniques we implemented and for all architectures. So let me go into some interesting findings which we can infer from these results. So first thing we observe is that ranking of architectures is not consistent across different self-supervised techniques. For example, if you look at rotation, then it may appear that RevNet is the best architecture, but then if you implement relative patch location, then it seems like ResNet v1 performs really well and RevNet is not that good. You can see these results from different angle and observe that ranking of different self-supervised techniques is not consistent across architectures. So for example, if you use ResNet v2, it may appear that rotation is better than predicting relative patch location. However, if by chance you use ResNet v1, that it looks like relative patch location is much better than rotation. So the main message here is architecture matters a lot in self-supervised learning. We also look at the performance of different layers, and we observe quite interesting thing. So for all architectures which use skip connections, it seems like your representations get better the deeper you go. However, it's not the case for, let's say, AlexNet or VGG, where we observe that when you get close to the final layers, the performance dramatically drops. So we believe that this is very important observation because a large fraction of previously proposed techniques were actually evaluated either on AlexNet or VGG, and those they may report suboptimal performance. Finally, we compare our results to the results reported in the literature. So for the 4 self-supervised techniques which we re-implement, we show that results can be boosted a lot just by using the proper architectures with large capacity. And we also observe that we get actually quite competitive number if we compare across wide range of previously reported numbers.
Right, so now that we know how to get better performance in self-supervision, we can look deeper into multiple of the aspects that were part of our study. For example, one aspect was that, Alex said, we use the different widening factors of the network, right? But when you make the network wider, you also make the representation larger that you take out of the network because there's many more filters. So that could be actually a confounding factor, and we wanted to check, is it actually the representation size that matters or the network capacity, the width that matters? So for one specific instance of these experiments, we control both of these separately, explicitly, and actually both matter, as you see here. Like bottom right, which is the widest network and the largest representation, is by far the best. But varying each of them individually deteriorates as they get smaller. Now, you could say that, okay, we use very large data sets with lots of labels for the evaluation, like ImageNet and places. Maybe actually having huge representation is very bad if you go to tasks where you have much fewer labels, right, which is where self-supervision hopefully matters more. So we tested that also. We evaluated on small portion, with only small portion of ImageNet, small portion of places, which is this bright bar. And no, even for using few labels, larger representation performs better in all cases, for all models, all self-supervision tasks. So that was one thing to look into. Another one is that one could argue, okay, the way we evaluate the representation is by checking if a linear model can use this fixed representation to perform classification. But there is no reason that the features, even they might be useful but not linearly separable, possibly. So we tested if this commonly used linear classification way of evaluating makes sense, or maybe it doesn't make sense at all. So here we performed the evaluation using a MLP also, which is the full line, and the linear classification is the dashed line. And as you can see, the dashed line and the full line follow pretty much the same patterns, and the ranks don't really change between them, which means, yes, this linear evaluation is actually a useful thing to do, and doesn't seem misleading for all the models that we tried. Then, when we do this unsupervised learning of representations, then we do the evaluation, we suddenly use a lot of labels. And this is not really what we would like to, because, I mean, then what's the point? But the question is, how do you select a model, especially if you have multiple models, maybe multiple self-supervision methods, and you can train them unsupervised, but how do you choose which one to use at the end of the day? And we looked at one possible way, which is to look at how well the model performs in the pretext task that you trained it with. And this turns out not to be a good indicator. So we have here in the x-axis the pretext task performance, y-axis the downstream performance. And this example here, the model that performs best on the pretext task is actually miserably bad on the downstream task. So this is an open question. And for now, we still need the labels in the end for model selection. Now going back to the thing that Xiaohua showed previously, the timeline of models. This is where we were at. And then with the intuition from the previous experiment, since we need the labels anyways, it might make sense to just get the labels and then see how we can use them during training, right? And this brings us into the semi-supervised setting, where we have another poster here in the workshop. Like if you use a few labels and insert them into a self-supervision training pipeline, you can get much better representations. And just for info, even if we use all the labels, if you add some self-supervision losses, actually you can get quite a boost. So if you work on self-supervision, we suggest that you also evaluate your self-supervision method in the semi-supervised and in the fully supervised setting even. And then recently there was other works, for example, especially the people working on CPC, which you will hear about right after that, I think. I think they came to the same conclusion. They also evaluate the CPC method in all these three settings. Yeah, so that's it. We provide code at this GitHub URL for all the experiments. You can download pre-trained models if you want to just look at the representations without training them, and we have Colab that lets you play with it. Thank you.
Well, thanks for the great talk. I guess we can have time for one question. If anybody wants to ask a question, please come to the mic, maybe. All right. So maybe I can ask one question. So you said that the different architectures, like different network architectures, are better for different type of self-supervision. You show it. Does it consistently exist across these different data sets, like for ImageNet places and so on? Is it the same curve that you see, or same performances?
I would say that yes. So at least we tried on places data set. Mm-hmm. And then we just, in our paper, we have a plots one-to-one of ImageNet performance and places performance, and they look exactly the same. So it's a mess, like the architectures cross a lot, across different methods, but then at least the picture looks exactly the same on two different data sets.
Thanks a lot.
Thank you.
Our next talk is data efficient image recognition with contrastive predictive coding. And Olivier is going to be presenting this one.
Okay. Well, yeah, I first want to thank the organizers for putting together this terrific workshop and for giving me the opportunity to present our work. So the impetus for this project is the simple observation that recent success in machine learning has extensively relied on vast amounts of supervision, either in the form of large labeled datasets or rewards coming from a computer simulation. And this draws a stark contrast with humans and animals who are able to reach very strong performance on a wide variety of tasks, in fact, with very little supervision. So just to drive this point home, let me focus on the task of visual classification and tell you that this particular breed of dogs is a Rhodesian Ridgeback. Most of you will now likely be able to tell me that all of these other images also contain Rhodesian Ridgebacks. So the goal of our project is going to be to try to build a recognition system which approaches the efficiency of human observers. So in order to get at this question, we started out by simply evaluating the efficiency of modern recognition systems. And so what I'm showing you on the y-axis is the test accuracy of a ResNet 152 architecture given varying amounts of labeled images to train from. And so what we can see on the right side of this graph is that when given the entire ImageNet dataset, this architecture reaches a very strong performance of 95%, but when given less and less amounts of labeled images, performance drops, going down to a mere 40%. And this is despite the fact that we varied a large number of hyperparameters in order to try to rescue the performance of this model. So for example, we changed the amount of regularization, data augmentation, and model capacity in order to try to save this model's performance, and this is what the best that we found. Now, just as a reminder, human observers lie in the top left corner of this graph here. So our job is going to take this curve and try to push it as much as possible in the top left corner of this graph. So we hypothesized that human observers achieve this remarkable efficiency by making good use of the vast amounts of unlabeled images they have at their disposal, and that makes up our everyday visual experience. And since unlabeled images are just as accessible to artificial systems, we figured this would be a valid way of trying to build an efficient recognition system. And the particular unsupervised or self-supervised objective that we chose to focus on is contrastive predictive coding, which looks for a stable structure in images by predicting the representation of one part of the image from that of other parts in the image. So specifically, we're going to take an image and divide it into a grid of overlapping patches like so, and encode every one of these with a convolutional network which terminates with a mean pooling operation, leaving us with a single feature vector for this particular patch. Doing so for all patches gives us now a field of feature vectors, and we're going to train this representation by using the feature vectors which come from the top of the image in order to predict those at the bottom of the image. So specifically, we're going to use a context network to aggregate all of the feature vectors that lie above a certain level, and in this case, the midpoint of the image, and use this row of context vectors in order to predict patches that are below that point. Now, having trained the network in this way, we can now discard that context network and use this field of feature vectors as a representation for downstream tasks. Now, what's remarkable about the CPC objective is that although it is entirely unsupervised, a simple linear classifier trained on top of it achieves a very strong classification performance, surpassing 60% top one, which in fact is greater than a full-blown AlexNet architecture trained on image pixels. So encouraged by these results, we decided to take this objective into the efficient classification problem. So the first modification we're going to bring to this setup is replace that linear classifier on top of the representation with a more powerful ResNet architecture. But as previously, I'm only going to show this ResNet architecture, the classifier on top of the CPC objective, a small number of labeled examples, whereas the CPC representation has the entire unlabeled ImageNet dataset to learn from. And the upshot of this procedure is a very different picture from the one that we were seeing previously. So because we're using a powerful ResNet architecture on top of the CPC representation, in the big data regime, we're able to match the performance of fully supervised networks. However, given that we are soaking up so many of the free parameters in our representation with this unsupervised objective for which we have a lot of data, we suffer a lot less as we go down into the low data regime. In fact, we maintain a 20% improvement in this setting over our supervised baseline. But at this point, since we're using the entire unlabeled ImageNet dataset, whereas the supervised baseline only has access to the small number of labeled examples that we're giving it, we decided to also compare our approach to other means of semi-supervised learning. So here I've simply zoomed into the low data regime. And so generally, semi-supervised methods fall into two broad classes, the first of which is very similar to ours in that it uses a self-supervised learning mechanism in order to learn representation and then transfers to classify a small number of labeled examples. So instance discrimination, exemplar learning, and rotation prediction are three examples of this that have been used for semi-supervised learning. And what we see is that these objectives are actually not sufficient in order to attain the results that we get with CPC, nor do they surpass our supervised baseline. Now, these objectives have been extended by jointly training for both the supervised and unsupervised objectives, yielding impressive results, but these still fall short of the ones that we obtain. Now, a second class of methods for semi-supervised learning uses label propagation, which in a nutshell, tries to make better use of the small number of labeled examples that we have access to. And these can use pseudo-labeling, virtual adversarial training, or entropy minimization. But nevertheless, these methods fail to kind of approach the results that we're getting. So encouraged by these results, we decided to ask whether this representation could be usefully transferred to a separate data set with an associated task to it. And for that reason, we turned to image detection on the Pascal dataset. So this dataset has a small number of images, so around 10,000, which is similar to the low data regime that we were considering previously. So in order to get at this, we're going to simply replace the ResNet classifier on top of the CPC representation with a faster RCNN architecture, which outputs not only the class label, but also the position and size of the object. So just to get ourselves situated, other unsupervised objectives which attempt to transfer to Pascal usually reach around 65%. These methods can be improved either by training on larger unsupervised, unlabeled data sets like deeper cluster, or by combining multiple different objectives together. Now, our method, which uses a single objective and only trains on the ImageNet data set, improves upon these methods by a wide margin. Now, what's even more exciting to us is that this performance is now approaching the one that you get by training supervised on ImageNet before transferring over to Pascal. And I want to stress the importance of this result, because if we were to close that gap, then that would mean that we would no longer need large annotated data sets for transfer learning. In fact, large unlabeled images would be sufficient. So to conclude, we found that contrastive predictive coding can be usefully applied in the semi-supervised learning setting, giving large improvements over both supervised baselines and competing semi-supervised methods. And we think there's a variety of ways of extending this that we would be very happy to talk to you about. Thank you for your attention.
Thanks for the great talk. And so we have time for one question, if we have a question. Do we have any question? Right, maybe I go for the question. So what about when you combine CPC with other self-supervised objectives? Did you try it, like combination of them with CPC?
So we haven't tried that yet, but we think that CPC actually lends itself fairly naturally to making predictions over a variety of different transformations of the image. So right now we're mainly considering translation, but you could imagine extending that to rotation, dilation, and so on. We're very excited to try that.
Thank you. Thank you very much. So this concludes our contributed talk session. Now we're going to have the coffee break and the poster session. And after that, we're simply going to be here 1 hour later with great 3 speakers, Andrew Zisserman, Olivier Scherfros, and Abhinav Gupta.